Hello there, and welcome to this video on polar coordinates in 2 dimensions. You might be wondering, why do I need to use polar coordinates, or why do I need to know polar coordinates? One good reason is because it can simplify the maths on occasion, especially when you're doing integration, or if you're integrating over a surface. Sometimes using polar coordinates can simplify the function. In polar coordinates, it might be easier to do. Another reason why polar coordinates are useful is because not every function can be easily expressed in Cartesian coordinates, but in polar coordinates, certain expressions can be. In this video, I'm going to be showing you how you can convert from Cartesian coordinates into polar coordinates and the inverse functions as well. To begin, if we have a look at the diagram, we can see we have point P expressed as an x and y coordinate. However, in polar coordinates, we get point P with an angle between x and y and a line with length r, or we could call it a radius. I'm going to show you how to go between the Cartesian coordinate system into the polar coordinate system. Using trigonometry, I'll be able to derive the identities that will help you go between Cartesian and polar. So let's start by writing down SOHCAHTOA. Now I'm going to label the sides. So where theta is the opposite side, the y would be the opposite, r would be the hypotenuse, and the x will be the adjacent. From here, to express x in terms of r and theta, well, we have a and we have h. Looking at SOHCAHTOA, we can use cos. Therefore, cos theta is a over h, which is x over r. If we then make x the subject, x is r cos theta. And we can do exactly the same for the y coordinate. So if we look at SOHCAHTOA, we've got O and H, so we can use sine. Therefore, sine theta is y over r, which when we make y the subject, y is r sine theta. And these are the identities that you can use to go between the Cartesian and polar coordinates. For completeness, I'm going to do the inverse identities, where I'm going to express r and theta in terms of x and y. R here is the hypotenuse, therefore I'm going to be using Pythagoras' theorem. R squared is x squared plus y squared, making r the subject. R is x squared plus y squared to the half, or you could just square all of it. To find theta in x and y, we have the opposite and the adjacent, so going back to SOHCAHTOA, we can use tan. Therefore, tan theta is y over x. If we rearrange to make theta the subject, theta is inverse tan y over x. Another useful thing to know will be how to calculate the area in polar coordinates. So if we show the area in Cartesian coordinates, the function fxy dA for area, is expressed as a double integral of the function dx dy. Now if we draw a diagram, we can see how this is expressed in polar coordinates. Here's the x and here's the y-axis. I'm just going to draw a segment of a circle. And we'll see how you express polar coordinates in the area. From this diagram, you can see that we've got the length r. But if we want to decrease or increase that length, we need to include the r. And to get the sweep of the angle, we have d theta. This means in polar coordinates, we express the area as, now remember it's polar coordinates, so it's a double integral because it is an area of the function in polar coordinates, and it will be r dr d theta. I'll be doing another video just to show you a few examples of how you can use this, but for now, here is just the identities, and this is how you go between the Cartesian coordinate system and the polar coordinate system in 2 dimensions.